The impulse momentum theorem defines momentum. There is no other way to define momentum. So when I say momentum, note that this immediately says change in momentum, and that's equal to P2 minus P1. P1 being the initial, P2 being the final, and this change in momentum is caused by what we call an impulse. We define this impulse as j of t, which is a function of time, and this is by definition the area of f of t versus t curve. This is the definition of momentum right here. So if you've been saying this in the past, that this is the momentum, the impulse momentum theorem defines a momentum like this, and you use the word momentum, then I'm going to say, wow, well done. I expected that's not what happened. So let's keep moving. So now there's a few things that we want to talk about. I think we want to talk about three things so that we can move quickly through this. The first thing, if I start to interpret this, now remember, this is review, so we've already done this. So if I go a little bit fast on my writing, that's why. What we said here is that only changes in momentum are meaningful. And it seems kind of strange. I keep saying this here. In other words, we need a reference momentum to define momentum. And that argument that I just said here sure does seem circular. Conceptually, momentum is like height. Height by itself, it's meaningless. Height has no physical meaning whatsoever. So when we use the word height, what do we mean by that? Well, let's imagine that we have a table here. And what we're going to do here is that we have a box. So let's say that I have this box right here. And what we're going to do here is that what we say here is that we say we're going to lift this box up some height. So when you make a statement that you've lifted a box some height, note what this is telling you that is that you are automatically making a reference to the ground. Right? Because if I move this box, let's say up to this height, right? So if I lift it up to that height right here, what we're really talking about is we're talking about the change in height. That's what's physically meaningful. So height by itself is meaningless. Momentum by itself is meaningless. A height change is meaningful. A momentum change is meaningful. So momentum by itself is meaningless. So if we now look at how this chapter is broken up as, you're going to see that everything revolves around the impulse momentum theorem. So conceptually, with bar diagrams, we write the impulse momentum theorem like this. We say that we have a change in momentum. And that change in momentum equals P2 minus P1, which is then equal to the impulse. And the only meaningful impulse is an external impulse, just like an external force. Now, if we mathematically solve for momentum 2, then we get P1 plus J external looks like this. So the way the chapter is broken up is what we're doing here is that we focus on a single object. So if you focus on a single object, then what you're going to find here is that the external impulse is not zero, and therefore momentum, you know what, I'm going to move this over because I'm running out of space. Let me move this over here. So here, momentum changes. And in other words, P2 is not the same as P1. You can see that if J is not equal to 0, then P1 and P2 must be different. That's if I focus on a single object. As soon as we finish this, we now focus on a system of particles. And in this case here, it turns out that our external forces that we look at are going to sum to 0. And if they sum to 0, then what we find here is momentum is constant, which then means P1 and P2 are the same. So if I focus on a single object, then momentum changes. If I focus on a system, we're going to find that the total momentum doesn't change. Okay, so we'll finish. We've already completed the first part. We just haven't done any examples. And then the third thing that I want to remind you here is I want to talk about what is an impulse. And what we found with an impulse here is that what we said here is that forces during collisions vary with time. So it's not a constant force, it's a variable force. And what we mean by this is that if I look at an image that I've already showed you here, you can see that this is what I'm talking about. I'm going to have to bring this right here. So what you're seeing here is that this is frame number 1, this is frame number 5, and then this is frame number 3. So when you're looking at these, what you're finding here is that there is a baseball that's moving in this way. And as a consequence, these guys start to interact. And in frame 3, what ends up happening is the speed of the ball is dropped to 0, and the ball completely stops momentarily. And then the ball changes direction and it comes in from the left and it goes out to the right. So what we said here is that by definition, the impulse is the area of a time-dependent force versus time. And the way we looked at this thing here is that we said, imagine that I have a curve something like this. Now, remember what I said here. These curves are typically not symmetric like this. So what I'm seeing here is that I could have an impulse that looks very smooth like this. They're typically not smooth. And what you're seeing here is that during this time here, the ball is going through states of compression. So in other words, this is going from state 1 all the way to state 3. And what we're going to see here is that at this point right here, the bat applies a maximum impulse when I'm plotting f of t here. So at this point, we expect here that the speed of the ball to be 0. Now what happens is that in theory, we should have very symmetric curves. In reality, that doesn't happen. But because we're in make-believe land here, we're going to say that it's symmetric. So now we get the expansion. And if we get the expansion, then the ball started from rest now, then speeds up all the way to frame 5. So if I'm looking at this thing, what we're seeing here is that this area of this curve is what we mathematically call the impulse. There is no constant force terms in the collisions. And by the way, I didn't state this, but I should state this right now. This is where right here we have contact begins. Right here we say contact ends. And then finally, this distance, time distance from here to here, delta t here, is what we call the contact time. Now, from the mean value theorem of integrals, we can replace this curve. That means we can choose a curve where it's, so if I look at its interval, which is this here, so it has the exact same contact time. So these guys are exactly the same, but the difference now is that we can choose a rectangle such that the area of this rectangle is exactly the same as a force versus time curve. In other words, I have to choose the height of this rectangle so that both of these curves have the exact same area. If we do this, this is what we call the average. I'd be careful here. I should say the time averaged force. And so what the fundamental theorem of integrals then says, it says that the impulse, which is the area of this curve, which is typically quite complicated because you have to parameterize a curve that's not nicely uniform like this. this is equal to the average, time average force times my contact time. This is what the impulse is telling us. And it turns out that the second curve is the most useful to deal with mathematically. Okay, let's go to the example.